Welcome to another open learning session where I'm going to catch up with deep learning. I'm working on this textbook called The Mathematics of Machine Learning. It's an open MIT book. The link is in the description. So last time we saw how we can actually calculate the inverse of a matrix using the Gaussian elimination technique. And now we are having this next chapter, algorithms for solving a system of linear equations. In the following, we briefly discuss approaches to solving a system of linear equations of the form AXB. We make the assumption that a solution exists. Okay, that makes maybe life easier, I guess. Should there be no solution, we need to resort to approximate solutions. How can you approximate a solution if it does not exist? Okay, we do not cover this in this chapter, but how could you actually approximate something which does not exist? I don't know. One way to solve the approximate problem is using the approach of linear regression, which we discuss in detail in chapter 9. In special cases, we may be able to determine the inverse such that the solution of AXB is given as x equals the inverse times b. Okay, that makes sense. So if you plug the x into AXB, then you will have A times the inverse, which is just the identity matrix, which means it's a nothing burger. And then you just have b equals b. So you could actually just say, once I have the inverse of the matrix, the solution is always inverse times b. Yeah, that's clever. That makes sense. Yes, there's always a catch, huh? However, this is only possible if A is a square matrix and invertible, which is often not the case. Otherwise, under mild assumptions, A needs to have linearly independent columns. We can use the transformation. And the transformation is AXB, we transform it so that we add the transpose on the left side. Okay. Then we factor out A transpose A and move it to the right side of the equation. And then we will just have X is equals to this part here. Yes, that makes sense. I will have not like a real intuition here, but I can say that from just using the transformations, you can write it like that. Interesting. This part here is called the Moore-Penrose pseudo-inverse. To determine the solution that solves AXB, which also corresponds to the minimum norm least square solution. A disadvantage of this approach is that it requires many computations for the matrix-matrix product, and computing the inverse of transpose A times A. However, for reasons of numerical precision, it is generally not recommended to compute the inverse or pseudo-inverse. Okay, I guess our computers are not made for that. Like, once the numbers are too small, then we will lose precision. In the following, we therefore briefly discuss alternative approaches to solving systems of linear equations. So the Gaussian elimination plays an important role when computing determinants, checking whether a set of vectors is linear independent, computing the inverse of a matrix, computing the rank of the matrix, and determining the basis of a vector space. Gaussian elimination is an intuitive and constructive way to solve a system of linear equations with thousands of variables. However, for systems with millions of variables, it is impractical as the required number of arithmetic operations scale cubically and the number of simultaneous equations. Okay, So it's impractical once your matrix is too big, because the number of operations just get too large too fast. And it scales cubically, so it's with the size of the matrix. So this basically, so what they're saying is, yes, here's a system how you can solve it, but don't use it for deep learning. It's too slow. But actually, we do not really need to know like the most performant way. We just need to have an understanding what the matrix operation is and what these kinds of operations are important for deep learning. And then we just use whatever substitute of technique there is. It's mostly hidden behind some kind of a library. I think it's called the BLAST library, which is really super fast for doing linear algebra and math and stuff and like that. So if it works and it's behind an API, I do not really care what technique it is. Important is that we actually know what happens in the mathematics part of the deep learning. Okay, so let's just move on. In practice, systems of many linear equations are solved indirectly by either stationary iterative methods, such as the Rickardson method or the Jacobi method, the Gauss-Seidel method, or the successive or relaxation method, or Krylov subspace methods. Man, so many methods, huh? Conjugate gradients, generalized minimal residual, or biconjugate what? Conjugate gradients. Oh my god. Okay, so there are many different techniques, blah blah blah. And the key is that the key idea of these iterative methods is to set up an iterator of the form. Okay, so you have some kind of a equation which is running in some kind of a loop. Here you can reuse the matrix C and reuse the vector D. And you just need to exchange the variable X. And what they're doing is somehow they reducing the error in every iteration, so X converges to the solution. Okay, we will introduce norms, which allows us to compute similarities between vectors. I guess this is just a random sentence. Oh no, it's because of this one, the error. Okay, so I guess this is just more like an infomercial part. This transformation is quite interesting, that we can have like this general, what is it called, Moore-Penrose pseudo-inverse. If we have that, we just plug B in and then we have the solution. But this one is super expensive. That's why we don't want to do it. And our Gaussian elimination play is also super expensive once the matrix is large. So both ways are actually computational inefficient. Interesting. Like, oh man, there's so many people working on this. Like every single part, every single piece. Just like making like these, like just one kind of operations more faster. It's like, and then once you have it, then your name has been there forever. Then it's called, I don't know, the Rickardson method, for example. All right, I think this is it. Chapter 2.3 is done. This was a long chapter. The book is quite deep or dense. We will have many more videos to go through. Okay, so I will make a cut here. Thank you very much and see you next time.